together, when you would run a system that would rely on the OpenSplice cache, you would have this concept of the working set, the prefetched data. In some system, you will have a portion of prefetched data. On some other system, there won't be at some point any more space for taking advantage of prefetching. In some other system, you will want to say that you will always want to keep some amount of space for prefetching, and then you can perhaps customize the cache replacement strategy by using simply a random strategy on some cache, or a custom strategy on yet another cache, or a simple fully associative replacement strategy in yet another cache. So the bottom line is that, again, you can get started by using a very simple API, but then there are lots of knobs that allow you to configure this cache to really get very, very high performance and really minimize, if not reduce at all, the cache misses, and ensure that most of the time you will experience local heat as opposed to remote heat. Okay, so now that we've seen this, let's try to quickly take a look at the architectural style that you could implement with this cache. So one is what we call typically the symmetric caches. This is typically used whenever you have a system that is built out of symmetric nodes, which means nodes that more or less have all the same computational power as well as the same memory size. So in this case, it makes sense to have cache that have similar size on each node, and the resulting system is really peer-to-peer, because in this case, there is no preference for one node or another when trying to resolve a remote heat. And so you have a very well-balanced system, and which will behave very nicely in terms of load balancing and overall performance. But if you have a very asymmetric system in which you have a mixture of very embedded systems or systems with very limited, let's say, resources, well, it could be things such as embedded system, microcontroller, or let's say even handheld devices. Okay, then you have somewhat of a challenge, as I was describing before. And the OpenSplice cache actually allows you to cope with this challenge by making it very simple to define a set of nodes that, as we call them, typically behave as a super cache. So these super cache are not running a server. They are just some caches that can be configured to have much higher memory size, and moreover can be configured so, for instance, to partition the key space. So that's just configuration on a typical cache. And if you do that way, for instance, by partitioning your key value in three, or perhaps with some overlap, there are several different strategies you can use. You can have very good properties in terms of load sharing, in terms of load balancing, and so on. And as I was explaining before, you can also have very good properties in terms of capacity misses, because if we take as an example this resource limited or resource constrained node, if its working set exceeds, let's say, 2 cached value, it can surely have space in this super cache for storing the extension in its working set and resolving it through remote heats, which is very good. So again, you can use the symmetric as well as the asymmetric topology, and the way in which you configure it really depends on the needs of your system and the type of hardware on which you have to deploy this system. Okay, so now moving to the concluding remarks. In terms of availability, as announced last Monday in our press release, this technology will be generally available on Q1 2009. Programming languages will be C++ and Java, and initially the supported operating system will be Linux and Windows, with more operating systems coming later in 2009. If you want to engage soon on a technology evaluation or a sneak peek, or discussing specific needs, we will be more than happy to do that, and please engage with us as soon as possible. Now, concluding this webcast, so again, OpenSplice Cache is a very innovative caching technology that, as we have seen throughout the webcast, as an architecture that has been designed bottom-up to ensure maximum performance, practically by construction. So as you have seen, I went through the key performance equation of every caching technology, and that equation is really applicable to hardware cache as well as software cache, and I showed you how our architecture really optimizes and minimizes all the key parameters in that equation. OpenSplice Cache leverages the OpenSplice EDS high-performance messaging middleware for implementing its distributed consistency protocol. And this is very important because by leveraging OpenSplice EDS, we didn't have to reinvent our own protocol for reliable multicast. We didn't have to optimize, and make production industrial strength coherency protocol. I mean, we are leveraging from our own technology, a technology that is deployed today in air traffic control system, in fast trading system, high-frequency trading systems, risk management, combat management system, and so on. And we have taken this bulletproof technology and used it as the backbone for implementing a very high-performance coherency protocol below that federates our cache instance. So, it's very rock solid, it's very efficient, and it's really exploiting a value-add architecture. Other important point is that architecturally we can support equally well symmetric system as well as a highly asymmetric system. And indeed, you can really deploy the OpenSplice Cache in embedded system because our memory requirements are not so much beyond that of the minimal layer of OpenSplice EDS, which is around 1 megabyte. So you can still be able to deploy this solution as far as you have, a few megabytes to allocate to do it, which is pretty good. So I would like to conclude finally the webcast by quoting what has been said already about this technology. So Massimo Pezzini, which is a Gartner VP and fellow application platform strategist, for this specific technology quoted that distributed caching technology is emerging as an enabler technology for a variety of scenarios, including high-performance computing, extreme transaction processing, complex event processing, and cloud computing. And after a year of incubation, distributed caching platforms are entering mainstream adoption. And again, OpenSplice Cache is an example of this. Caching technology will be increasingly at the foundation of user application infrastructure, and this will be driven by the business imperative to reduce cost and boost performance and scalability in that intensive application. So why reduce cost? So one aspect in which caching technology can be key in reducing cost is because, well, first of all, they reduce the traffic to your data backend. And as I motivated in the beginning of my presentation, if you can reduce the data flow to your database, that means that you don't need to upgrade it. And typically upgrading those is really, really expensive, while caching technology typically have far more competitive both initial entry, let's say adoption level pricing, as well as total cost of ownership. And the other advantage of reducing cost is that this technology typically allows you for far cleaner architecture, which in the end reduce your maintenance cost as well as development cost. The boost of performance, I think it was very well explained by the webcast and motivated by the overview of our architecture and how it has been really designed for maximum performance. So before concluding, some references and online resources. You can visit our website for getting more information about OpenSplice EDS and the OpenSplice Cache. We have quite a few WebEx recorded and ready to be seen on our website. We have recently launched a YouTube channel which covers OpenSplice related technologies, and we'll soon have some videos on the cache as well. We have blogs, and then we have, as usual, the standard related website. So thanks a lot for being with us tonight. And well, I would like to give you my most sincere seasonal greetings. So soon will be Christmas for some, Hanukkah for others, so best wishes for everyone, and the most sincere Happy New Year and great 2009 to everyone. So